You know, when we talk about greenhouse gas emissions, our minds usually jump to cars or power plants. But what about the absolute giant in the room? The industry that literally moves 90% of everything you own across the globe. Today, we're going to get into the real deep science of why cleaning up global shipping is such an unbelievable challenge. We're talking about the fundamental laws of chemistry and physics that lock this industry into its current path. Okay, so here's how we're going to break it all down. First, we'll get a handle on just how big shipping's carbon problem really is. Then, we'll dive straight into the science, the unavoidable chemistry of the fuel, and the tough physics of moving a giant steel box through water. After that, we'll see how it all plays out in a real-world trip, looking at the huge trade-off between speed and pollution. And finally, we'll zoom out to see the true carbon cost of a single voyage, from the oil well all the way to the ship's wake. All right, let's set the stage. Global shipping is the quiet, indispensable engine of our modern world. No question about it. But running that engine comes at a pretty steep environmental cost. To even begin to talk about solutions, we first have to wrap our heads around the sheer size of the emissions problem.
So here it is, the big number. According to the International Maritime Organization, back in 2018, maritime shipping pumped out 1,076 million tons of greenhouse gases. Now, to put that number in perspective, that's almost 3% of all human-caused emissions on the planet. That's about the same as a major industrial country like Germany or Japan, and it's way more than all of global aviation combined.
And where is all this coming from? Well, this is where it gets really stark. Almost 80% of the energy that powers international shipping comes from one thing: heavy fuel oil, or HFO. Think of HFO as the thick, sludgy leftovers from the oil refining process. It's cheap, it's packed with energy, but man, is it carbon intensive. This almost total dependence on one type of fuel is really the heart of the whole decarbonization challenge. And that brings us to the core of this whole explainer. See, the reason shipping is called a hard-to-abate sector isn't because of a lack of trying. It's because it's running headfirst into the unyielding constraints of science. We're talking about fundamental principles of chemistry and physics that you just can't argue with. And what's wild is that these same principles are what make the system so cheap and effective, but they're also what make it so dirty. Let's start with the chemistry, at a concept called the carbon factor. Now, it is absolutely critical to understand that this isn't an efficiency rating you can improve with a better engine. No, this is a fixed chemical property baked into the fuel's molecules. When you burn a hydrocarbon, a molecule of hydrogen and carbon, you're just forcing a chemical reaction with oxygen. For every single atom of carbon in that fuel, you are going to get one molecule of CO2. You cannot change that ratio. It's basic chemistry. And here's the number that rules the entire game. The official carbon factor for heavy fuel oil is 3.114. Just think of it like a conversion rate. It means for every 1 ton of this fuel you burn, the laws of chemistry guarantee that you will produce 3.114 tons of carbon dioxide. It's a non-negotiable chemical fact.
Just let that sink in for a second. How on earth can the exhaust weigh more than the fuel you put in? Well, the answer is in the atoms. See, a carbon atom has an atomic weight of 12. Oxygen has an atomic weight of 16. So when one carbon atom from the fuel grabs 2 oxygen atoms from the air, you get CO2. The new molecule's weight is 12 plus 16 plus 16, which is 44. So the CO2 is way heavier than the original carbon. The ship is literally grabbing mass from the atmosphere as it moves. The emissions aren't just some byproduct. By weight, they are the main thing being produced. Okay, so now let's add a physics problem on top of that chemistry problem: energy density. This is just a fancy way of saying how much punch is packed into a certain amount of stuff. You can measure it by weight, megajoules per kilogram, or by volume, megajoules per liter. For a ship that has to cross an entire ocean without stopping for gas, you need to cram as much energy as possible into the smallest, lightest space you can.
So this slide gets to the question everyone asks: why not just use batteries? Well, let's look at the numbers. A really good top-of-the-line lithium-ion battery pack gives you about 0.9 megajoules per kilogram. Heavy fuel oil? It gives you about 40 megajoules per kilogram. That's more than 40 times the energy for the exact same weight. To get the same range, you'd need a battery that's over 40 times heavier than the ship's fuel tanks. That battery would take up so much space and weight that you couldn't carry any cargo. The economics would just completely fall apart. The gap is it's enormous.
All right, so we've got a chemical reaction we can't change and an energy density problem we can't solve with today's tech. Let's see how these principles smash into reality by looking at a single container ship on one of the busiest routes on the planet, Shanghai to Los Angeles. But before we look at the numbers, you have to understand this one crucial bit of physics.
The power you need to push a ship through the water goes up with the cube of its speed. So why the cube? Well, the resistance, or drag, is proportional to the square of the speed. And power is just that resistance force multiplied by the speed. So speed squared times speed gives you speed cubed. What this means in the real world is brutal. To go twice as fast, you need 8 times the power, which means you're burning fuel at a much, much higher rate. It's called the cube rule, and it is unforgiving. Okay, now this table shows you exactly what that cube rule does to your fuel tank. Let's take a big container ship. If it's cruising at a pretty fast 20 knots, the trip takes about 12 days, and it's burning 250 tons of fuel every single day. You do the math, multiply the fuel by the days, then by that magic carbon factor of 3.114, and you get about 9,200 tons of CO2. Now just watch what happens when the captain slows down to 17 knots. The trip takes less than 2 days longer, but because of that cube rule, the daily fuel burn just plummets to 154 tons. And this chart just makes it crystal clear. The fast trip, at 20 knots, is that big bar on the left, 9,200 tons of CO2. The slower trip, even though it took a bit longer, is the much smaller bar on the right, just 6,600 tons. The difference is 2,600 tons of CO2 saved on one single trip, just by pulling back on the throttle. So here's the bottom line. A 15% cut in speed from 20 knots down to 17 gives you a whopping 28% reduction in total CO2 emissions for the voyage. This is why slow steaming is one of the most powerful tools we have right now to cut shipping emissions. It perfectly illustrates that tension between the business need to deliver things fast and the environmental need to slow down. When it comes to ships, managing your speed is managing your emissions. So you might be thinking, okay, 6,600 tons for the slow tribe. Got it. But that's not the whole story. The pollution coming out of the smokestack is only the final chapter. To get the real picture, you have to look at the entire life of that fuel. And that's where this concept of well-to-wake emissions comes in. It's basically a full life cycle accounting. It has 2 parts. First, there's tank-to-wake, which is what we've been calculating, the emissions from actually burning the fuel on the ship. But then there's the second, hidden part, well-to-tank. That counts all the emissions from pulling the crude oil out of the ground, refining it, and transporting it to the port, all before a single drop even gets into the ship's tank. So let's just walk through that journey real quick. It starts at the well, with all the energy needed for production and refining. Then you've got to get it to the tank on the ship, which takes more energy. And finally, you get the wake, which is the combustion on board. The true carbon cost is the sum of all 3 of those steps. Okay, so let's go back to our slower voyage. If we apply a standard life cycle factor, which is around 1.21 for this kind of fuel, we account for all that upstream stuff, including things like methane leaks. So we multiply our 6,600 tons of CO2 by that factor, and the real total is closer to 8,000 tons of CO2 equivalent. That E is important. It means we're now counting other greenhouse gases too. It just reveals this whole hidden layer of carbon cost that's built right into the fuel supply chain. And this quote from the analysis we've been looking at it really hits the nail on the head. It says, shipping is hard to clean up because it depends on these super energy-dense fuels and on operating physics that literally punish speed. That's the trap, right there. The very things that make the whole system work so well, packing a ton of energy to go really far, are tied directly to the chemistry and physics that create all the emissions. So that leaves us with this massive question for everyone from engineers to policymakers. You've got an industry where the chemistry of its fuel guarantees huge amounts of carbon, and where the physics of moving through water means that going faster, which is what business wants, is in a direct fight with the environment. When you're cornered by science like that, how do you even begin to steer this enormous, essential industry toward a zero-carbon future?